Hi, and welcome back. This is section 2, and we're going to focus on processing time series data because it can be different from other types of data you've been using so far. Time series data is data that is captured in chronological sequence over a defined period of time. Introducing time into a machine learning model has a positive impact because the model can derive meaning from changes in the data points over time. Time series data tends to be correlated. This means that there's a dependency between data points. This has mixed results for forecasting. This is because you're dealing with a regression problem, and regression assumes that data points are independent. You need to develop a method for dealing with data dependence so you can increase the validity of the predictions. In addition to the time series data, you can add related data to augment a forecasting model. For example, suppose you want to make a prediction about retail sales. You could include information about the product being sold, such as item identification or sales price, along with the number of units sold per time period. The third type of data is metadata about the data set. For instance, say that you have a retail data set. You might want to include metadata, like a brand name or a genre for music or videos, so you can group results. It's better to have more data. When you work with multiple data sources, you'll face the challenge of handling the timestamp of the data. You'll observe differences in the timestamp format and other challenges such as incomplete data. However, you might be able to infer missing data in some cases. For example, say you have some data that contains both the month and the day, but no year. Observe whether the data seems to sequence through the month numbers in the database, repeating after 12. If it does so, you could add the year if you knew when the data started. You could then infer future years based on the order of the data. Much timestamp data is stored in UTC format, but not all data is. You should check if the timestamp is in local or universal time. Sometimes the timestamp doesn't represent the time you think it does. For example, suppose you have a database of cars that were serviced at a garage. Does the timestamp indicate the time the car arrived, was completed, or picked up? Or does it indicate when the final entry was entered into the system? Say you're trying to model the hourly caloric intake of patients. However, you only have daily data. Then you'll need to adjust your target timescale. Also, your data might not have any timestamps. There could be other ways to extrapolate a time series depending on the data and domain. For example, you might have wavelength measurements or vectors within an image. As a final note, remember that daylight savings is different around the world. Also, because of daylight savings time, might even occur twice a year in their time zones. A common occurrence in real-world forecasting problems is missing values in the raw data. Missing values makes it harder for a model to generate a forecast. The primary example in retail is an out-of-stock situation in demand forecasting. If an item goes out of stock, the sales for the day will zero. If the forecast is generated based on those zero sales values, the forecast will be incorrect. There are many reasons why values can be marked as missing. Missing values can occur because of no transaction. They can also occur because of possible measurement errors. For example, a service that monitored certain data wasn't working correctly. Or as another example, the measurement couldn't happen correctly. In retail, the primary example for an inability to take correct measurements is an out-of-stock situation in demand forecasting. This means that demand doesn't equal sales on that day. There are several ways you can calculate the missing data. The first method is forward fill. This uses the last known value for the missing value. Building on that idea, moving average uses the average of the last known values to calculate the missing value. Backward fill uses the next known value after the missing value. The danger here is that you're using the future to calculate the past, which is bad in forecasting. This method is also known as look ahead and should be avoided. Interpolation uses an equation to calculate the missing value. You can also use a zero fill. This is often used in retail because missing sales data shouldn't be calculated. The missing data represents that there were no orders on that day. It would be wise to investigate why this happened, but in this case, you don't want to fill in the missing value. You might get data at different frequencies. For example, you might have sales data that includes the exact timestamp the sale was recorded, but have inventory data that only contains the year, month, and day of the inventory level. When you have data that's at a different frequency than other data sets, or data that's not compatible with your question, you might need to downsample. Downsampling is moving from a more finely grained time to a less finely grained time. As the example shows, this could be converting an hourly data set to a daily data set. When downsampling, you need to decide how to combine the values. In the previous case of sales data, summing the quantity makes the most sense. If the data is temperature, you might want to find the average. Understanding your data helps you decide what's the best course of action. The opposite of downsampling is upsampling, when you move from a less finely grained time to a more finely grained time. The problem with upsampling is that it's extremely difficult to achieve in most cases. Suppose you want to upsample your sales data from daily sales to hourly sales. Unless you have some other data source to reference, you wouldn't be able to do this. There are cases when you need to do something, perhaps to match the frequency of another time series. Or you might have an irregular time series or specific domain knowledge that would help. In those cases, you need to be careful how you make the conversion. For the retail example, the best you could do is create a single order for the day at a specified hour. For temperature, you could copy the daily temperature into each hourly slot, or use a formula to calculate a curve. In data science, outliers have a mix of positive and negative attributes. The same is true of time series data. Suppose you were examining sales data and you had an order that has an unusually high number of items. You might not want to include that in your forecast calculations because the order size might never be repeated. Removing these outliers and anomalies is known as smoothing. Smoothing your data can help you deal with outliers and other anomalies. There are a few reasons why you might consider smoothing. First, during data preparation, you remove error values and could also remove outliers. You might also want to smooth your data to generate features. For visualization, you could smooth your data to reduce the noise in a plot. It's important to understand why you are smoothing the data and the impact that it might have. The outcome might be to reduce noise and create a better model. But an equally important question is, could your smoothing compromise the model? Is the model expecting noisy data? Will you also be able to smooth the data in production? That's it for part 1 of this section. We'll see you again for part 2, where we'll review more time series specific challenges and the tools and algorithms. Hi, welcome back. We'll continue exploring wrangling time series data. Seasonality in data is any kind of repeating observation where the frequency of the observation is stable. For example, in sales, you typically see higher sales at the end of a quarter and into the fourth quarter. Consumer retail sees even higher sales in the fourth quarter. Be aware that data can have multiple types of seasonality in the same data set. There are many times when you should incorporate seasonality information into your forecast. For instance, localized holidays are a good example for sales. The chart shows that the total revenue generated by arcades has a strong correlation with the number of computer science doctorates awarded in the US. But correlations do not mean causation. If you disagree, see the source for the chart. There are many other correlations plotted on the site, and none of them make any sense. With your own data, be careful that you're not seeing and acting on correlations that don't have meaning in the real world. Here's an experiment. If you generate two random time series data sets of numbers between 0 and 1, you'll find that they have a very low correlation. But if you introduce the same slope to both data sets, you'll see a very strong correlation. You need to know how stable a system is. The level of stability, or stationarity, can inform how much you should expect the system's past behavior to inform future behavior. A system with low stability won't be successful at predicting the future. You'll often want to determine the trend for a time series. But if you adjust the series for the trend, it can be difficult to compare it with another series that was also adjusted for the trend. This is because the trends might dominate the values in the series. This could then lead to overestimates in correlation between the two series, like we discussed previously. Autocorrelation is one of the special problems you face with time series data. As you've seen in other machine learning problems, the goal of building an ML model is to make sure you're separating the signal from the noise. Autocorrelation is a form of noise because separate observations aren't independent of each other. A time series with autocorrelation might overstate the accuracy of the model that's produced. Some of the algorithms you'll look at in this module can help correct for autocorrelation. These factors, along with seasonality, will influence the model you'll select to produce your forecast. Some algorithms handle seasonality and autocorrelation, but others do not. PENDAS was developed with financial data analysis in mind. As such, it's good at handling time series data. First, you can set the index for your PENDAS data frame to be a date time. You can then use date and time to select your data. You can use ranges that contain partial dates. You can also extract date parts such as year, month, weekday name, and more. For grouping and resampling tasks, PENDAS has built-in functions to do both. Finally, PENDAS can give you insights into autocorrelation. For more information about PENDAS and the time series, refer to the PENDAS documentation. One of the tasks in building a forecasting application is to choose an appropriate algorithm. Your choice of algorithm should be determined by the type of data set you're using and the features of that data set. Amazon Forecast supports these 5 algorithms, but there are others. Each algorithm can handle data with slightly different characteristics. For example, take autoregressive integrated moving average, which is also known as ARIMA. It removes autocorrelations that could influence the pattern of observations. Or take exponential smoothing, which is also known as ETS. This algorithm is useful for datasets with seasonality. You can find out more about these algorithms in the Amazon Forecast documentation. Some key takeaways from this section of the module include time series data is sequence data that includes a time element which makes it different from regular datasets. Some of the time challenges include dealing with different time formats, handling missing data through downsampling, upsampling, and smoothing, dealing with seasonality such as weekdays and yearly cycles, avoiding bad correlations. PENDAS has excellent time series support with functions for dealing with time. There are 5 algorithms used by Amazon Forecast: ARIMA, DeepAR+, ETS, NPTS, and Profit. That's it for this section. We'll see you in the next video. Hi, and welcome back. In this section, we'll look at how you can use Amazon Forecast to create a predictor and generate forecasts. When you generate forecasts, you can apply the machine learning development pipeline you've seen throughout this course, but you still need data. You need to import as much data as you have, both historical data and related data. You'll want to do some basic evaluation and feature engineering before you use the data to train a model so you can meet the requirements of Amazon Forecast. To train a predictor, you need to choose an algorithm. If you're not sure which algorithm is the best for your data, Amazon Forecast can choose for you. To do this, select AutoML as your algorithm. You also need to select a domain for your data. If you're not sure what the best fit is, you can also select a custom domain. Domains have specific types of data they require. When you have a trained model, you can then use the model to make a forecast using an input dataset group. After you've generated a forecast, you can query the forecast. You can also export it to a bucket in Amazon S3. And finally, you can encrypt the data in the forecast before exporting it. The overall process for working with Amazon Forecast is to import historical and related data. Amazon Forecast inspects the data, identifies key data, and selects an appropriate algorithm. It uses the algorithm to train and optimize a custom model and produce a predictor. You create forecasts by applying the predictor to your dataset. You can then retrieve these forecasts in the AWS Management Console, or you can export the forecasts as comma-delimited files. You can also use an API and AWS CLI commands to create and retrieve forecasts. When you work with Amazon Forecast, you can select the domain you're working in. There are domains ranging from retail to web traffic, and there's also a custom option for everything else. By selecting a domain, you improve the efficiency of the predictor. Each domain has specific types of data that you'll supply when you build the predictor. For example, the retail domain expects data for the item identifiers, a timestamp for the observation, the number of sales for that item, and the specified timestamp. Here's an example of the data you'd need to provide for a retail demand forecast. For the time series, you need the time when the transaction took place, ideally in UTC format, the item ID of the item, and how many items were sold. The metadata for the item might include the category, the item color, and other attributes. The link back to the time series data will be only the item ID because item metadata typically doesn't change. Related data for creating a more useful forecast could include the sales price or other promotion data. To link this back to the item, you must include the timestamp and the item ID. Here's an example of the data you'd need to provide for a web traffic forecast. For the time series, you need the web page ID, the number of page views per month, and the timestamp. Related data for creating a more useful forecast could include the page category, such as navigation or content category. You'll also need the geographic identifier for the web client. For metadata, you might also need to provide the region and the sales promotion information. Amazon Forecast predictors use an algorithm to train a model. They then use the model to make a forecast using an input dataset group. To help you get started, Amazon Forecast provides predefined algorithms: ARIMA, Deep AR+, ETS, NPTS, and Profit. You can also use the AutoML feature. It will try all the algorithms to see which one's the best at predicting data. When you prepare data for training and machine learning, you typically hold back data to use when you validate and score the model. The data that you hold back is usually a random sample of your available data. With time series data, you must process your data differently because of a correlation between time. When you import your data, Amazon Forecast breaks it into training and test data sets, which the diagram shows. The training data is used to train the model, which is then tested against the data that was held back. You can specify multiple backtest windows, which will split the data multiple times, train the model, and use metrics to determine which model gives the best results. The default backtest window is 1. You can change how Amazon Forecast splits the data by setting the backtest window offset parameter when you create the predictor. If you don't set this value, the algorithms use default values. After you've trained a model, you will need to measure its accuracy, which you'll learn about next. The first Amazon Forecast evaluation metric is the weighted quantile loss, or W quantile loss. When Amazon Forecast creates a forecast, it provides probabilistic predictions at 3 distinct quantiles: 10%, 50%, and 90%. These prediction quantiles show you how much uncertainty is associated with each forecast. A P10 quantile predicts that 10% of the time, the true value will be less than the predicted value. For example, suppose that you are a retailer. You want to forecast product demand for winter gloves that sell well only during the fall and winter. Say that you don't have sufficient storage space and the cost of invested capital is high, or that the price of being overstocked on winter gloves concerns you. Then you might use the P10 quantile to order a relatively low number of winter gloves. You know that the P10 forecast overestimates the demand for your winter gloves only 10% of the time, so you'll be sold out of your winter gloves for 90% of the time. A P50 quantile predicts that 50% of the time the true value will be less than the predicted value. Continuing the winter gloves example, say you know that there will be a moderate amount of demand for the gloves, and you aren't concerned about being overstocked. Then you might choose to use the P50 quantile to order gloves. A P90 quantile predicts that 90% of the time the true value will be less than the predicted value. Suppose you determine that being understocked on gloves will result in large amounts of lost revenue. For example, the cost of not selling gloves is extremely high, or the cost of invested capital is low. In this case, you might choose to use the P90 quantile to order gloves. Amazon Forecast also calculates the associated loss, or error, at each quantile. Weighted quantile loss calculates how far off the forecast a certain quantile is from actual demand in either direction. Lower W quantile loss metrics mean that the model's forecasts are more reliable. The root mean square error, or RMSE, is another method for evaluating the reliability of your forecasts. Like W quantile loss, RMSE calculates how far off the forecasted values were from the actual test data. The RMSE finds the difference between the actual target value in the dataset and the forecasted value for that time period, and it then squares the differences. The example shows how to calculate RMSE. The RMSE value represents the standard deviation of the prediction errors. This test is good for forecast validity when the errors are mostly of the same size. That is, there aren't many outliers. Lower RMSE metrics indicate that the model's forecasts are more reliable. Here's an example of how a web retailer might use the accuracy metrics to evaluate a forecast. The retailer wants to predict the demand for sales of a particular brand of shoes. They input the sales records for this brand into Amazon Forecast to create a predictor. The predictor provides a forecasted demand of 1,000 pairs with the P10, P50, and P90 values shown. The weighted quantile loss values indicate that 10% of the time there will be fewer than 880 pairs sold. 50% of the time, fewer than 1,050 pairs will be sold. And 90% of the time, fewer than 1,200 pairs will be sold. The retailer can then use these values to determine which level of inventory to hold. They can base their decision on their assessment of the risk that they won't be able to fulfill orders, or that they'll have excess inventory. Some key takeaways from this section of the module include: You can use Amazon Forecast to train and use a model for time series data. There are specific schemas defined for domains such as retail and EC2 capacity planning, or you can use a custom schema. You need to supply at least the time series data, but can also provide metadata and related data to add more information to the model. As with most supervised machine learning problems, your data is split into training and testing data, but takes into account the time element. Use RMSE and W quantile loss metrics to evaluate the efficiency of the model. That's it for this video. We'll see you in the next one. Hi, welcome back. It's now time to review the module and wrap it up. In this module, you learned how to describe the business problem solved by Amazon Forecast, describe the challenges of working with time series data, list the steps required to create forecast by using Amazon Forecast, and use Amazon Forecast to make a prediction. Thanks for participating. See you in the next module. Welcome back to AWS Academy Machine Learning. This is Module 5, and we have a great topic for you today, computer vision. In this module, we'll start with an overview of the computer vision space, and you'll learn about some of the use cases and terminology. Next, we'll explore details about analyzing image and video with managed services from Amazon Web Services, or AWS. Finally, we'll look at how you can use your own customized data sets for performing object detection. At the end of this module, you'll be able to describe the use cases for computer vision, describe the Amazon Managed Machine Learning services available for image and video analysis, list the steps required to prepare a custom data set for object detection, describe how Amazon SageMaker Ground Truth can be used to prepare a custom dataset. And finally, use Amazon Recognition to perform facial detection. Thanks for watching. We'll see you in the next video.